Test, test. Good? Okay.
Do you usually hit that button with the airways?
We usually do, yeah, the smiling face.
All right, I think we'll get started. I'm pleased to introduce Gary Douberly. Gary is from the University of Georgia, where he is part of the Department of Chemistry and Physics and a recent Associate Dean of the Franklin College of Arts and Sciences. Gary got his PhD in physical chemistry, chemical physics, in 2006 from the University of North Carolina, Chapel Hill. Afterwards, moved on to the University of Georgia for a postdoc and started a faculty position there in 2008. He's been there since, doing a lot of interesting things with helium nanodroplets, which we'll get to hear today. He was also a JILA visiting fellow about 6 years ago, and so he's a long-term JILan over the years. So hopefully we're going to hear some of his new stuff about the Einstein-Hunderthaus effect.
Well, thank you, Heather, for the very kind introduction and the invitation to come and talk to a Department of Physics. I don't really get to do this very often, so I kind of live in this strange zone where I interact with everybody from synthetic organic chemists to folks working in atomic, molecular, and optical physics. And so it's been a real good opportunity for me, a privilege to have a collaboration with Heather Lewandowski and to have been a visiting fellow in 2016, because I've really learned a lot about molecular physics because of those types of interactions. And so this is a bit of a strange title. I wouldn't use a title like this if I were talking to my chemistry colleagues, but hopefully I can tell you something that will spark your interest. It's related to, in the end, it's related to detailed fundamental interactions between molecules that are doped into superfluid helium droplets. And so if I show you kind of the bird's eye view of the way I think about the field of research to which I contribute, to which my group contributes, it's in this zone of chemical physics, right? And so ultimately the goal is to derive some microscopic understanding of chemical reactivity, right? What are reaction mechanisms? And so there's all sorts of things that play into this, and they all feed into each other in this loop. Quantum chemistry, computing potential energy surfaces, or measuring potential energy surface to some extent through high-resolution molecular spectroscopy, chemical dynamics and chemical kinetics. All of these things together inform each other in a way such that in the end we can understand something about chemical reactivity. So if I were talking to my chemistry colleagues and I tried to motivate my area of research, I would say we're doing molecular spectroscopy of reaction intermediates in the service of understanding reaction mechanisms. And so, for example, I might show some complicated thing like this, where on the left-hand side, for example, this is some detailed chemical reaction mechanism associated with the hydrocarbon oxidation chemistry that occurs in combustion. And you can see there's all these interesting radical molecular radical species that these are the things that I would call reaction intermediates between reactants and products. Or if we were to say what is going on in the gas phase chemistry associated with the troposphere, then one might look at a key player like the hydroxyl radical, OH, and all the various chemistry in which it participates. And so this is kind of the arena that we play in as molecular spectroscopists in this area of physical chemistry. Is we're trying to develop techniques to isolate interesting reaction intermediates so that we can learn something about their molecular properties, the molecular structure, and their physical properties. So the tool of choice in my group is this tool called helium droplet isolation spectroscopy. So I'm going to talk a lot about this today. And I'm going to discuss it in a way so that, in a way that is aimed at this audience, right? An audience that can appreciate perhaps the condensed matter physics type stuff that goes into the interaction between molecules in a superfluid helium droplet environment like this. But just to start off, I'll say that this technique is really it's marrying the ideas of two older techniques from the field of chemical physics, matrix isolation spectroscopy and molecular beam spectroscopy. And I already said some of this stuff, but we're really interested in using this technique as a way to do rational in situ synthesis of reaction intermediates, cool these things down to low temperature, and do molecular spectroscopy experiments on them. And also, one of the things that we've been able to show that this technique can be used for is the formation and spectroscopy of so-called entrance and exit channel open shell molecular complexes, meaning things that are weakly bound, that are held together by van der Waals forces that live behind small barriers, for example, to reaction. This low temperature environment allows us to stabilize those species and measure molecular spectra. So if one goes way back in the literature, so 1954, one finds really the first paper where George Pimentel from Berkeley discussed this matrix isolation technique. And so just to read off here, the matrix isolation method proposed here involves accumulation of a reactive substance under environmental conditions which prevent reaction. And that's the basic idea, is that so if this is some type of rare gas matrix, for example, solid argon or solid neon, then if these are some type of reactive molecules, then this provides an environment where you can trap these things and hold them apart, prevent them from interacting with each other, or perhaps on occasion they do. And so you have this matrix that is transparent over a broad region of the electromagnetic spectrum, so you can do spectroscopy experiments. You have low diffusion of the trapped molecular species, and you can stabilize reactive molecular species. You can take advantage of the low temperature to generate reasonably clean spectra of the molecules that you prepare in this environment. So this is kind of the basis of what one would call matrix isolation spectroscopy. On the other hand, if you go back in the literature, so this is 1974. This is a paper from when Rick Smalley was a postdoc with Don Levy at the University of Chicago. What we're seeing here is really one of the very first examples of the coupling of a laser to a molecular beam. And this really kind of kicked off this whole field of molecular beam spectroscopy. And you can really appreciate why this is nice, because this is NO2. If you look at this part of the visible spectrum of NO2, at 300 Kelvin, you get these broad absorption features. But if you look at it, and that's in some gas cell, but if you expand pure NO2 into a vacuum through some supersonic expansion, making a molecular beam, then collisional cooling in the jet leads to a reduction of the temperature, the ensemble temperature, and you get cleaner spectra. If you co-expand with argon, and then the collisional cooling in the jet leads to temperatures of 3 Kelvin, you get nice sharp resonances instead of these broad bands that are difficult to interpret. And so in 1992, Jacinto Scoles at Princeton University had this idea of marrying these two ideas, right? And so the basic concept here is that he's taking argon, expanding it in a supersonic expansion, but you can pre-cool this nozzle so that in this nozzle expansion you make large clusters of argon, right? And so instead of having this macroscopic bucket of solid argon in which you put molecules, his idea was to make clusters of argon, and then through a process that he called the pickup technique, you run these clusters through a gas cell, and then through the attachment of the gas molecules onto the surface of the cluster, you could make beams of these argon-doped clusters, and then do molecular beam style spectroscopy on it. So here, in this experiment, he's using a CO2 laser to do cluster beam photofragmentation spectroscopy. And by looking at the fragmentation of the cluster, you could see which wavelengths were resonant with the molecule attached to with the argon cluster. And so this is really the first example of marrying the idea of this kind of matrix isolation and molecular beams. And so here are some results from that experiment. The molecule that he was looking at is sulfur hexafluoride, and down around 940 wave numbers, so inverse centimeters, you have this quadruply degenerate antisymmetric stretching vibration that is very bright. And he took a line tunable CO2 laser and tuned through, and he was able to see the photofragmentation when the laser was in resonance with SF6 attached to the cluster of argon. And so he did various things where he co-expanded the SF6 with the argon versus picking it up out of this external gas cell, and you could see various changes in the spectrum. And so this was really the seed of the idea that led to helium droplet isolation spectroscopy. So this was July of '92. Later in that year, October of '92, they switched up the gas. They were expanding from the nozzle from argon to helium, and they did the same experiment with SF6 using this line tunable CO2 laser. But what they observed was very sharp lines, much sharper than the lines that they observed when they would attach the SF6 to clusters of argon. And so from this first experiment, they were able to determined that there was something special with these helium clusters. There's something about putting SF6 onto helium clusters that led to the sharpening and the cleaning up the spectrum that they were measuring. Now, again, they were using a line-tunable CO2 laser, so the resolution in this experiment is pretty poor in the sense that it's limited. You can only change the wavelength discretely. And so a few years later, this is actually my PhD boss, Roger Miller. He was on sabbatical in Göttingen working with Peter Tönnies, and they decided that they would take a tunable diode laser, like a lead salt diode laser operating in this region, and just tune over and use the same approach where they put SF6 onto a helium cluster and tune over this sharp transition here that Scoles measured with the line tunable CO2 laser. And this is what they observed. So the black trace is the experimental observation, and the red trace is a simulation based on an effective Hamiltonian model for a spherical top molecule. And so what is being observed here is you're seeing this quadruply degenerate vibration of the molecule, but you're also seeing changes in the rotational quantum numbers, right? So this is the so-called Q branch, which is no change in the rotational quantum number. And this is the R branch, where you add 1 quantum of angular momentum. And this is -1, where you lose 1 quantum of angular momentum. And so this is, for those who may not be used to seeing this, this is a rho vibrationally resolved infrared spectrum of SF6. And so that was quite profound at the time. They're like, oh wow, this molecule is in some type of symmetric environment. From the relative intensities of the lines, they could tell that the temperature was very low, which I'll get back to, and there was something very special about this environment that was allowing the system to exhibit some type of free rotation inside this matrix environment. Yes.
So in the beam, are the Doppler broadening small enough that you don't have to worry about it?
So the line broadening in the spectra are due to inhomogeneous mechanisms associated with the solute-solvent interaction. I'll come back to that a little bit, but like the laser is just crossing the molecular beam, so there's the Doppler broadening is very small in comparison to the other mechanisms that contribute to broadening. And so let me shift gears a little bit and say a little bit about how this spectrum is actually measured. So here's this low temperature nozzle. It's probably 15 Kelvin or so. And you make these droplets, and they're droplets, right? Because helium is a liquid all the way down to absolute zero under these conditions. And so you make these droplets through a homogeneous nucleation process, and then you pass them through the scattering chamber. This is the so-called pickup technique. And you capture molecules out of the gas phase. And then if you take laser light and you shine it like this, then if you tune in and out of resonance with various degrees of freedom of the molecule, you will put energy into the system, which will then, on some longer time scale, get transferred to the solvent, to the bath, and you'll get evaporation, right? And so this evaporation is detected as a change in the ionization cross-section of the droplet in an electron impact mass spectrometer. And so this is, like if this is some ion signal, then you see dips in the ion signal as you tune in and out of resonance of the molecule that lives inside of this droplet, right? And so this is an action spectroscopy technique that gets around the fact that the density is too low to do direct absorption, right? And so this is the technique. One of the interesting things about this is that you can design experiments where you do sequential capture. So in this simple cartoon that I've drawn here, you pick up this molecule twice and you make some type of molecular complex, right? But you can imagine all sorts of interesting ways in which you can sequentially combine things via this pickup scheme to create things inside of this helium environment. So the cooling timescale is fast. It's faster than the timescale between the various capture events, so you can really imagine this as one thing that's cold interacting with some other thing that's cold, evolving on some intermolecular potential energy surface. Just for a point of reference, if you have a helium droplet that has 10,000 atoms, which is very typical for these types of experiments, this evaporation process can dissipate about 6 volts of energy, right? And so this is on the order of like chemical bonds. So in principle, you can do bond-forming reactions in these droplets and then have something remaining downstream to probe spectroscopically. The evaporative ensemble temperature is 370 millikelvin, so the temperature is pretty low. So if I show you a slightly different picture from this one, I want to emphasize a couple of things about my own experiment that are a bit different. So in our experiment, if we want to look at molecular radicals, for example, related to combustion or atmospheric chemistry, the way in which we produce those species and dope them into these droplets is through a process called flash vacuum pyrolysis. This is an old technique where basically you're just heating up a precursor molecule thermally and it falls apart and you put the pieces into the droplet. And then we have schemes by which we can do various types of laser spectroscopy employing electric and magnetic fields to look at the Stark effect, the Zeeman effect, et cetera. And we have this mass spectrometry dimension as well. So in this region of the experiment here that I'm blowing up for you, we have a continuous wave optical parametric oscillator that's working in the infrared region, the mid-infrared. And then this defines some type of laser droplet beam interaction zone. And then we apply electric or magnetic fields perpendicular to the board. And then by exploiting the linear polarization of the OPO, we can align our laser polarization to be either parallel or perpendicular to the applied field, leading to various selection rules on the rotational quantum numbers. Here's a picture of a cell that we designed to do Zeeman spectroscopy. You have these permanent magnets, and then they're put in this arrangement so that you get a homogeneous magnetic field crossing the droplet beam, and then the laser light would go, bounce back and forth through these openings. And we can do the same thing here, all right? So let's go back to this spectrum. So the first rotationally resolved spectrum of a molecule in a helium droplet from 1995. So this really kicked off the whole field of helium cluster spectroscopy. There's a couple of things to note. One is that if you compare this spectrum to the spectrum measured in the gas phase, you observe two things. The frequency shift is to the red by about 1.4 inverse centimeters, and that's pretty small. It's small in comparison to the frequency shift you would measure if you put this molecule into solid argon, right? So the matrix shifts are small. And that is a universal property or a universal effect that we observe for molecules in helium droplets. The other thing that one observes is that the moment of inertia for rotation is larger when you put the molecule in helium, which may not be too surprising. You have the solvent environment that has to kind of move with the molecule to some extent as it rotates. And so you see this renormalization of the rotational constant, which means you get an increase in the effective moment of inertia for rotation. And also you measure through the Boltzmann distribution of rotational states, the cluster temperature. All right? So this is an important part of this talk. What is the mechanism by which this reduction in the rotational constant, how does that work? So here is another molecule that was seeded into, this is like the second molecule that was seeded into helium droplets. So this is a linear triatomic molecule, OCS, all right? Great, good molecule. It has an antisymmetric stretch right around 2062 wave numbers. And what's shown on top is a gas phase molecular beam spectrum of it. And you see, the delta J equals +1 and the delta J -1 transitions. So you see the rotational transition superimposed on top of the vibrational transition. And you can see that when you put this molecule into helium, you see a small redshift of the vibrational band origin, and you see this reduction in the rotational constant, meaning an increase in the effective moment of inertia through the change in the reduction in the splitting of these lines. Now that is a helium droplet that is composed of the helium-4 isotope. Now if you do the same experiment where you put OCS into a droplet composed of the helium-3 isotope, you get this, which doesn't look like this. And so the question is why? Well, right away, one might speculate that this has something to do with the bosonic nature of liquid helium, where the helium is the helium-4 isotope, right? So at the temperature of a helium droplet, 370 millikelvin, liquid helium is in the helium-2 phase. It's a superfluid. Whereas for helium-3, it's not. It's a fermionic fluid. It's a non-superfluid at this temperature. The temperature of a helium-3 droplet, the evaporative ensemble temperature for a helium-3 droplet is about 0.15 Kelvin, so 150 millikelvin. Not cold enough for it to be a superfluid. And this is shown here, right? So here's the phase diagrams, and here's the operative temperatures for this type of experiment. So one might think back to the two-fluid model from Lev Landau, right? And this classic experiment from Andronikashvili, where he looked at the periodicity of a stacked torsional oscillator in bulk liquid helium as a function of the temperature. And this is shown here in terms of this two-fluid model, where as you reduce the temperature, the superfluid fraction goes up and the normal fluid fraction goes down, right? So this is kind of the classic Andronikashvili experiment from the 1940s. And so one might imagine that you could devise an experiment of this type using a molecule inside of a helium droplet, where your molecule is your torsional oscillator and your droplet is your bucket of liquid helium. And so this is how an experiment like that works, and this was in this science paper from Toennies' group in '98. So you take OCS, once again, and you put it into a pure helium-3 droplet, and then you start to add back systematically some amount of helium-4, and you look for some change in the spectrum. And they coined this experiment the microscopic Andronikashvili experiment. And so this is the result. So if you look up at the top, you see this rotationally resolved vibrational spectrum for OCS in a pure helium-4 droplet. You see this broadened, blobby-looking thing for OCS in a pure helium-3 droplet. So the green is helium-3, the blue is helium-4. And then through the pickup technique, you can add back the helium-4. It has more mass, so it will cluster around the dopant. And then as you systematically add it back, you recover this rotational fine structure in the spectrum. And so increasing number of helium-4 going down. And so the line width, so to go back to this question about line widths, the line widths in these type of spectra are a few hundred megahertz. And the mechanism for the line broadening is inhomogeneous in nature because all the different aspects of how you create these beams of droplets, you create a statistical distribution of droplet sizes and things like this, so you get small shift depending on the size, so you get this inhomogeneous mechanism. But the conclusion from this 98, they went out on a limb and stated, the appearance of the rotational fine structure is a microscopic manifestation of helium-4 superfluidity. Okay, so then this was intriguing, and what does this mean exactly? And so I kind of put it in words, my own words, so please forgive me. So at 0.37 Kelvin, the helium-4 droplet is, in quotes, a superfluid, right? We're talking about a cluster, not a bulk. Superfluidity is a thermodynamic property of the bulk phase. Let's put it in quotes, a superfluid. But there's few thermal excitations populated at the temperature of the cluster due to this Roton gap, right, in superfluid helium. If we measure the spectrum instead in helium-3, you get rapid rotational diffusion, which leads to motional narrowing, and you get no rotational fine structure. Or, in effect, the embedded rotor is scattering off particle hole excitations in the liquid. And so that is presumably the difference between these two measurements. From a more cluster perspective, like thinking about this in terms of a cluster, if you have number of atoms on the x-axis here and energy on the y-axis, the lowest phonon mode of a cluster of a few thousand helium atoms occurs at an energy that is beyond, that isn't populated at 0.38 Kelvin, right? And so this curve right here is this kind of excitation spectrum, dispersion spectrum of the bulk superfluid. And here's the Boltzmann distribution at 0.38 Kelvin. So presumably, this L equals 0 lowest order phonon mode occurs at an energy that's too high to be populated at the temperature of the droplet. And all of the rotational degrees, all of the populated rotational states at this temperature, they live here under this Boltzmann curve. And so the coupling between them and the phonons of the droplet is sufficiently weak so that you can get these long rotational coherences and see the rotational fine structure in the spectrum. What is populated at the temperature of the droplet are the surface excitations of the cluster, and this is how molecules establish thermal equilibrium with the droplet through interactions with the surface. So as a summary, if I have some molecule like this, methyl fluoride, which is a symmetric top, I can do all of this stuff that you learn in molecular spectroscopy class as a graduate student. You can draw all these quantum states and attach all these quantum numbers to them and draw these arrows and label these transitions, right? And it all works. This is exactly what one would expect for the pattern. The pattern of lines is exactly what one would expect for an A1 symmetry row vibrational band of a C3V symmetric top, including all the nuclear spin statistical considerations, all of that. It's all in there. The caveat is there's this interesting renormalization of the rotational constant due to the interaction of the molecule with the helium environment. And so there was a lot of theory over the years to try to understand this. And so one of the major players in this arena was Brigitte Whaley at Berkeley. And they would do things, really incredible things like path integral Monte Carlo simulations of a molecule surrounded by 100 helium atoms, right? And really try to get at the microscopic nature of what was going on. And so basically, the free rotor behavior of the molecular rotation is preserved because of inefficient angular momentum coupling between the dopant and its quantum liquid surroundings. This is consistent with the superfluid character of the droplet. But then she goes on to say the molecule-helium interaction, right, because there is a non-zero interaction between the molecule and the helium environment, right? It's weak, but it's non-zero. The molecule-helium interaction appears to induce a local non-superfluid density component in the first quantum solvation shell. That would be like these red atoms in the vicinity of SF6. This can adiabatically follow the molecular rotation, resulting in a reduction of the rotational constant. So this was kind of the early description of the renormalization of the rotational constant, was this molecule is inducing a non-superfluid component of the solvent in the vicinity of the molecule, which then somehow rigidly rotates with the molecule as it's living in this larger superfluid environment. But when you start to look at this renormalization of the rotational constant, each dot corresponds to a different molecule measured. You see that it's all over the place, right? And one might naively draw some line through here. And in fact, if you're not careful when you're reading the literature, people will say, oh, it's just a factor of 3. Well, it's clearly not just a factor of 3. It's all over the place. And it depends on a couple of things. It depends on how large the rotational constant is in the gas phase. Over here, you have a large rotational constant, meaning a small moment of inertia, right? Fast rotation. And so in this regime, it almost appears as if the helium can't react to the rotating molecule and the two remain decoupled, right? There's the ratio is close to 1. But as you get into this so-called adiabatic following regime, the details of the molecule helium potential energy surface are clearly very important because it's essential in determining what this is, right? Up here, this is like benzene, right? And down here, you have some linear molecule or something. There's all sorts of scatter in here, and it depends on the molecule-helium interaction. So let me jump back to this because I want to motivate what I'm going to tell you for the rest of the talk. And yeah, looking at the time. So I'm going to tell you about the hydroxyl radical because I think it's a really interesting molecule, and this is a physics crowd, and so, you know, 2 atoms, hopefully that's not 1 atom too many, right? I mean, we've got 2 atoms, we're going to talk about the hydroxyl radical. But it, you know, just to kind of keep this in context, it is really an important species in all of tropospheric chemistry. It's really the detergent of the atmosphere, right? It's what initiates all the oxidation chemistry for all the hydrocarbons and other crap that gets pumped up into the atmosphere. And just to show you a couple of papers from my group which looks at various related species. So this is a paper that looks at the hydroxyl radical interacting with a methanol molecule. So this is methanol. And this happens to be one of these reaction intermediates along a hydrogen abstraction reaction pathway, which is one of 2 possible pathways for the chemical reaction. And without going into details of what we learned, it provided some insight into the low temperature kinetics associated with the reaction and how you get this kind of strange negative temperature dependence. You know, the rate constant for the reaction goes up as the temperature goes down. And so we were able to help the kineticists provide some fundamental insight into what they were seeing by looking at this type of species, making measurements, and saying something about the theory and the experiment behind this. Here's another example where we have the hydroxyl radical interacting with an acetylene molecule, so HCCH. And you have 2 low-lying electronic states that are coupled through a spin-orbit interaction, and you get the electronic angular momentum of the hydroxyl radical is partially quenched due to the differing intermolecular interactions for these 2 different types of states. And that is all imprinted into this high-resolution spectrum that we measured, and we were able to learn something about that interaction. But I'm going to just tell you for the rest of the talk about the hydroxyl radical itself. And so for those of you who may not think about this a lot, the hydroxyl radical is an open shell diatomic molecule. It has 1 free electron in a p-pi orbital. And so the electronic ground state, that's what X is for the ground state. It's a doublet pi 3/2 electronic ground state. All right? And there is a slightly higher in energy is a doublet pi 1/2 state, and then higher in energy, there's a doublet sigma 1/2. And so those 3 states are going to come into this conversation. And so when we put the hydroxyl radical into a helium droplet, we observe something that's quite frightening. We observe an anomalous lambda doubling. So I'll tell you what lambda doubling is. That's this slide right here. So if you have the hydroxyl radical and you have this electron in this p-pi orbital, if the molecule starts rotating, you know, in principle you can have, you know, kind of like a slippage of the orbital that the electron is in relative to the rotational motion of the molecule, basically a breakdown in the Born-Oppenheimer approximation, which physically is a coupling between the pi electronic state and the sigma electronic state, and that leads to something called L uncoupling, and that leads to a parity doubling of the rotational energy levels, and this emerges as so-called lambda doubling in the spectrum. So this is putting a quantum into the OH stretch, right? But no quanta into rotation, and you're really just seeing 2 different lines between the different parity components of the J3/2 state in the ground vibrational state and the J3/2 state in the excited vibrational state. So that's what we're observing here. And so those are the 2 lines in helium, and the dashed lines are the lines in the gas phase. And so, okay, what's the big deal? Well, okay, so one thing is that the hydroxyl radical is in this so-called fast rotor regime in the sense that the rotational constant, you know, the difference between this set of lines and this set of lines where you're going to J5/2, you know, that difference is very close to what it is measured in the gas phase, as you can see from these dashed lines. And that's kind of saying that, you know, from a first order approximation, the helium is just kind of staying out of the way of the OH as it's rotating in the fluid. However, the lambda doublet splitting is 5 times larger in the helium environment than it is in the gas phase. And so when we first observed this, we had no idea how to interpret this, because there's nothing you can do in your mind that would modify this interaction in the helium environment that would lead to this change, right? This sigma pi interaction, which leads to lambda doubling, can't possibly be modified to an extent that would lead to this observation. So there has to be something very subtle going on that's leading to it. And so the first thing we did was we exploited the Stark effect to disentangle the vibrational state-dependent lambda doubling. Because under zero field conditions, what you see here, the splitting experimentally, is just the sum of the lambda doubling in the two separate vibrational states, V equals 0 and V equals 1. And so to get at that, we take the different parity components of the J equals 3/2 rotational state, and we mix them with an electric field, right? And so the electric field mixes this stuff, and then now we can get allowed transitions that are E to E and F to F, which leads to nice spectra like this. So instead of 2 lines, you get many lines, and you can do this laser polarization trick to disentangle the different delta M selection rules. You can assign all this stuff, and then in the end, you can see what the lambda doubling is in both the ground vibrational state and the excited vibrational state. So we were confused, and this just made us more confused, because you see that there's a strong vibrational state dependence to this anomalous lambda doubling. We still don't understand the meaning of this. We think we understand the anomalous nature of the lambda doubling, but we don't understand this vibrational state dependence aspect of it. So if you think I'm going to explain that, I'm sorry, I won't. I can't. Okay, so what does this mean? All right, so what I'm showing to you here is, just focus on this picture over here. This is a hydroxyl radical with the p-pi orbital pointing perpendicular to the plane of rotation, and this fuzzy thing is a helium droplet, or in the plane of rotation. So really you have 2 different potential surfaces that you're dealing with, either A prime or A double prime. And these correspond to the, effectively to the different parity components of the rotation. And what we should expect is that the interaction, the helium molecule interaction, will be different in these 2 planes, right? There is some asymmetry, there's some asymmetry in the molecule helium interaction as you rotate about the plane of the molecule, right? And this is borne out in high-level theoretical calculations. So up on the top, we show quantum chemistry calculations of the potential of interaction between a single helium atom and OH as the helium atom is rotating around the OH, right? And so the red curve is for this A double prime surface, and the black curve is for this A prime surface, and the blue curve is for a closed shell analog, hydrogen fluoride, which is more like the A double prime surface. So you can see when the helium is interacting with the molecule in the plane of the singly occupied p-pi orbital, the interaction is stronger. And so if you compute using a helium density functional theory type approach, the helium density, atoms per cubic angstrom on the y-axis and the same x-axis, you see that for the A prime potential surface, the helium density is both larger and more structured, all right? And so one might generate a hypothesis from this and say that the effective moment of inertia for rotation here should be larger than the effective moment of inertia for rotation like this. Meaning that the molecule really has 2 different rotational constants, depending on whether or not it's in the E or the F parity quantum states. And this was our hypothesis that we used to build a Hamiltonian model using the gas phase Hamiltonian, but the only difference was that we allowed the rotational constants to differ slightly for the, this is actually a 6 by 6 matrix, but you have a 3 by 3 for both E and F parity components. We allowed the rotational constant to differ a little bit depending on whether or not you're talking about E states or F states. And sure enough, it doesn't take much. If they differ by just a small amount, less than 1%, you can, well, to the extent that the difference in the effective moment of inertia is a thousandth of an AMU angstrom squared. So this is a really tiny effect, but you can recover this splitting that you observe in the spectrum. Now, this is very phenomenological, but it provides at least some basic physical understanding of what might be going on. You have these two different ways in which the molecule can be interacting with the helium, and you get two different effective moments of inertia that leads to this anomalous lambda doubling. Now, this is not completely satisfactory because it's not a really good theoretical model, but I think it gets at the heart of the phenomenon. Now, we become more confused when we start to look at the Zeeman effect of OH and helium. So here are the zero-field states, and here are the states when you apply a homogeneous magnetic field on the order of 0.425 Tesla. And these are all the quantum numbers, selection rules. And in the spectrum, here's the zero-field spectrum. These are the lambda doubling components, the F to E and the E to F transitions. And here are the lines under the influence of the magnetic field. And you can write down very simple equations to estimate, things like the G factor of the electron given this observed splitting. And you can do this a little more carefully, use a full variational treatment of the interaction between the molecule and the magnetic field. You get the same answer as the simple analytical expressions. But what you can see here is that the prediction is the splitting is 0.317 wave numbers, and the observation is 0.379 wave numbers. This is way outside the error of the experiment. And in fact, what this corresponds to is a 21% increase in the G factor of the electron when the molecule is immersed in the superfluid helium environment. So now we're like really confused. All right, so we have this anomalous lambda doubling, we have this vibrational state dependence of it, and we have this anomalous Zeeman splitting that is showing us that there is this 21% increase in the G factor of the electron. So I was confused for several years, and I just left this kind of in the drawer. And then I met someone that really helped me try to understand this finally. His name is Misha Lemeshko. He's a theoretical physicist at the Institute of Science and Technology in Austria, near Vienna. And he has developed this quasi-particle theory called angulon theory. And he has used it to look at the quantum many-body dynamics of things like electron to lattice angular momentum transfer and things like this. And so, this paper was in 2019, and I became aware of it a couple years after this, actually, because I'm not reading these papers. But he's like, hey, we might have a way to understand the rotation of your OH molecule in a superfluid helium environment, because I have this method that looks at it's basically like a rotationally invariant quantum many-body theory that simplifies the understanding of things like angular momentum transfer between electrons and a phonon bath of the material that the electron is embedded in. And so this is related to this thing called the Einstein-de Haas effect. So I'll read this. In 1915, Einstein and de Haas and Barnett demonstrated that changing the magnetization of a magnetic material results in mechanical rotation and vice versa. At the microscopic level, this effect governs the transfer between electron spin and orbital angular momentum and lattice degrees of freedom, understanding which is key for molecular magnets, nanomagnetic mechanics, spintronics, and ultrafast magnetism, right? So basically, this is all conservation of angular momentum, right? This is off of Wikipedia. If you take a ferromagnetic material, maybe you do this in some of your physics undergraduate laboratories or something, and you apply a magnetic field that polarizes the electrons in the ferromagnetic material, then you can induce mechanical rotation in order to conserve angular momentum, right? And so this I'll come back to this a little bit at the end. But what about this angulon quasi-particle theory that he's employing? So this is basically the idea. You have a multi-orbital atom that has spin and orbital angular momentum, that's this, and then you have this phonon field which can carry angular momentum, right? And then if you put these two things together, right, you dress this guy with this guy, in the lingo, I guess, then you create this thing, which he's calling an angulon particle, and this is the basis of his theory. And so he has this. We go to this next slide here. And so what he's showing here is static effects of phonon dressing in this theory, quenching of orbital angular momentum by phonons. Different components of angular momentum as a function of the dimensionless electron-phonon coupling strength, which is this x-axis, electron-phonon coupling strength. Due to the coupling, electronic orbital angular momentum is reduced and phonon angular momentum emerges while the total angular momentum is conserved, right? This is just like the Einstein de Haas effect, right? And so you see that here where you have this orbital angular momentum that's going down. You see this angular momentum emerging in the material due to the phonon coupling, but the total angular momentum is conserved. And in addition to this, he shows that there is a renormalization of the electron G factor as a function of the dimensionless electron-phonon coupling strength. And this is because you're taking angular momentum out of the atom part of the equation, I guess. And so the G factor scales inversely with that angular momentum. So the less of it, the more the G factor is in appearance. And so can we apply this to, and I apologize for all the math and the equations, but I'll just talk through this. So can we apply this theory, Lemeshko's theory, to an OH molecule and a helium droplet? Because we're also seeing this weird renormalization of the G factor. And indeed we can. So there's a lot of heavy lifting here, but in the end, one can write down what appears to be a relatively simple Hamiltonian. And basically the idea is, in the bath of the liquid helium, the Hamiltonian can be written with additional angular momentum lambda, and that's not related to this lambda doubling. It's just an unfortunate coincidence. We're using the same Greek letter here, but it could be written with this additional angular momentum lambda, the momentum of the bath, right? So the idea is that the molecule inside the helium, through molecule phonon coupling, is going to lose some of its angular momentum and transfer it to this phonon bath. And you can parameterize this Hamiltonian and work out all of the matrix elements and whatnot, and derive an effective Hamiltonian that leads to parameters that, or you can then adjust the parameters to fit the experimental measurements. And so what he did was he said, okay, first, let's find, and it's a single parameter model, really, actually it's 2 parameters in the end, but starting out, it's a single parameter model, and this alpha is reflective of the molecule phonon coupling, right? And so the value of this alpha is adjusted to reproduce this renormalization of the G factor that's measured experimentally. And then what he does is he recognizes my original hypothesis that the interaction with the helium should be different for molecules like this versus molecules like this. And so that would imply that, also in this model, the molecule phonon coupling should be different for molecules like this versus molecules like this. So he writes down 2 slightly different ones. So if you start off with, say, 0.09, and then you adjust to reproduce this lambda doubling, then this is still maybe not completely satisfactory, but we're making better progress because now with this roughly a single parameter model, we can reproduce both this renormalization of the G factor of the electron and this anomalous lambda doubling that's observed. And so I guess in summary, since I'm right on time, is that this angulon quasi-particle theory shows us that we can think about the interaction of a molecule and a helium droplet fundamentally as a transfer of angular momentum between the rotor and the helium bath, right? This kind of like coupling between the phonon field of the droplet and the natural angular momentum of the dopant that's residing inside. And of course, for this specific system, you have to recognize that there's a few % difference between this angular momentum transfer for E versus F because of these different interaction potentials. But this ultimately can account for both of the experimental observations. And this avoids, this is something, this theory can be like, the time that it takes to diagonalize a 6x6 Hamiltonian. This is the theory, right? This can allow us to understand this complicated interaction between the molecule and the helium droplet, and this should be compared perhaps to some of the earlier theories that were trying to do explicit many-body quantum theory through path integral Monte Carlo simulations and things like this, right? Which are also useful and valid in my view, but this is a really nice approach to try to gain understanding of what we're observing. And so that's my physics talk. That's my physical chemist trying to give a nice physics talk. I appreciate, once again, the invitation to come and speak. I really love Boulder. I love coming back here. It's a real privilege to come back to Boulder. And with that, I'll acknowledge the various folks that have contributed to this work and the funding agencies, and thank you for your attention.
Great, thank you. Questions? Leo?
Yes, you quoted this value of lambda, 0.19, I think, or whatever. Yeah, 0.198.
Yeah, that's the ground.
So that's in units of h bar?
That's in units of wave numbers, my bad. Yeah, sorry.
Is this angular momentum?
This is the splitting. So this is the splitting between the lines in the experimental spectrum in units of centimeters -1.
Well, I'm confused. So I see lambda and Hamiltonian.
Yeah, I know. And I apologize for the unfortunate coincidence of parameters, but yeah, the operator in the Hamiltonian is the angular momentum of the bath, but this lambda, my apologies, is the lambda doubling in the experimental spectrum. Yeah.
You had a picture that showed how the renormalization of D and helium depends on the value of D.
Yes.
And high D is rotating rapidly, and the helium can't really deal with it.
Yeah.
But I would sort of think that classically, I want to ask how fast the thing is rotating value of D map, but then so does the outer value of J. So I would think, well, that our fourth transition would be rotating faster than our two transitions. So I would think if this is how I want to understand that, wouldn't I expect to see the rotational spectrum of all sorts of weird coordinates?
Yeah. No. Yeah. So what we. So this is exactly right. So, not unfortunately, but because the temperature is low, you can only measure so many lines. But this is exactly what we observe for larger molecules where we see this rotational fine structure. We see unphysical distortion constants, which is what you're getting at.
Yeah.
And it's because, like this angular momentum transfer that I'm talking about in the end. Now, I think this theory really has legs because we can go back and really try to understand why are these higher order terms in the rotational Hamiltonian so crazy. And it's because as you go to different values of J, you have different amounts of this angular momentum transfer, and you have different molecule-helium interaction potential, simply put. Every rotational state has a different interaction potential. And the amount of angular momentum so the good thing about this theory is that it is rotationally invariant, right? He does this unitary transformation into the rotating frame of the molecule. And this non-superfluid component that we talked about early in this field, this is the angular momentum generated in the solvent, right? Right? Like if I'm a molecule and I have this rotational wave function, then in kind of the frame of the molecule, I'm like, things are moving with me, but it's like a static picture if you're in the frame of the molecule, and it's like all this stuff that's kind of like stuck to it based on the molecule-helium interaction potential. But that should depend on the J quantum number, right? And so you should expect that your gas phase rotational Hamiltonian should be garbage, and it is.
Very interesting, Gary. So when you have OH in a helium droplet, it's not rotating very much. You're only populating quite low rotational levels. would think of that as probably 0.1 unit time of momentum rotation. So, can you, ideally, to test this model, you would want to warm it up potentially and see whether that still works, whether
Right.
molecules rotating it still produce the lambda doublet. But I guess there isn't any way that you can actually do that. You just warm it up.
Well, you can by exploiting the dipole moment, the electric dipole moment selection rule for the rho vibrational transition, right? So now it is rotating, right? Because J is equal to 3/2, even at 0 Kelvin, right? And so I would argue that in some strange way, it's rotating, right? It has 3/2 is the quantum number for its total angular momentum, right? I understand that that's a collection of effects from orbital and spin and whatnot, but if you if you excite this thing, right, at 3650 wave numbers, that's what this broad thing is, you're putting, that's the so-called R3/2 transition, so you're going up to J equals 5/2. So at least you can exploit the electric dipole selection rule to access that rotational state, right? So you get 2 in this experiment. And what you see here is that, you know, the scale is different, right? This is 1 wave number, and this is 10. So why is it so broad and nasty? What is going on? What is happening here, we think, and you can see the lambda doubling is you can't measure it because it's washed out by this broadening. What we think is happening is that the separation between J equals 5/2 and J equals 3/2 in the excited vibrational state is like, I don't know, 30 wave numbers or something, 20, I don't know. It's some large number of wave numbers. And at that energy, you have a continuous spectrum of phonon excitations to which that rotational energy can dissipate into the quantum fluid cluster. And so what you get is you get rapid rotational relaxation, so to say. So the rotation is just, you know, there's the decoherence is immediate, right? You get this Lorentzian type broadening as a result of the fact that you can have effectively resonant energy transfer out of the rotational degree of freedom and into this continuous spectrum of phonon excitations. And so you lose that. So unfortunately, you know, this lambda doubling is only emerges in this Q3/2 transition where you don't change the rotational quantum number upon vibrational excitation. If you have better idea, like maybe some type of stimulated emission pumping or something that could access higher ones, then yeah, maybe.
Great. I think we're at time, so let's thank Gary again.
Thanks.
Super physicsy.
Good, and clear and slow, lots of background.
Yes. You should turn yourself off.
Hot mic.